video, we are going to look at why does blood flow change. And so we're looking at the work of a French scientist, and he developed a formula that calculates blood flow, and there are 4 variables that are impacting this, and that is the viscosity. Viscosity is the thickness of your blood, and that's represented by V in the formula. The vessel length, and so that's the uppercase L in the formula. Your blood pressure, which is uppercase P in the formula, and the vessel radius, so how big around the vessel is that the blood's trying to flow through, which is the R, and that has the 4th power on it. And all of these constants came together, or all of these variables came together with a constant of pi over 8. And so there is this combination going on there of both direct and inverse variation. So directly proportional, inversely proportional, and the idea of a constant that we've been talking about with the concept of proportionality. So we are going to go to this app, and then this app is connected for you in your Canvas site so that you can use the app. And in the app, we are going to first off set the radius to be 3, the viscosity 3.5, and the length to be 50. So bringing this over, this is what the app looks like when you open it. And so we are to set the radius, which is the second slider here, to 3, the viscosity to 3.5, and the length to 50. Right. Now, what we're going to do next is the values that are in the chart that's here in our PowerPoint. So we are going to start off with the blood pressure being 20. And when the blood pressure is 20, we see that the flow rate, which is up here where my cursor is pointing at the top of the graph, is 3.6353. So here in our PowerPoint, we're going to write in what that flow rate is. So give me a moment here. 3.6353. And now we're going to go back to our app. Oops, wrong file. There we go. And we're going to change that blood pressure up to 60. Right? So when we change that slider to 60, I see that over here the flow rate has changed dramatically. So it is now 10.9058. And then I'm going to continue in this pattern. So I'm going to go to the app, and I'm going to change the blood pressure slider up to 100. I'm going to write down my number, change it to 140, write down my number, change it to 180, write down my number. So I'm going to write in all those numbers, and then we'll take a look at our data. So this was 18.1764. Next one was 25.4469. And the final one was 32.7174. So I am looking at my data, and what I am observing is that each time blood pressure got higher, so blood pressure was going up every time. And then I look at my flow rate, and I notice that each time the flow rate also got higher. So when blood pressure went up, flow rate went up. That's the relationship that I'm noticing between these 2 variables. So the first letter here, letter B, while exercising, a person's blood pressure will rise. What is the impact on blood flow? Well, from observing the trend in my data, that means that blood flow will increase, which is exactly what your body wants. And that's why it's increasing your blood pressure, because it wants that additional blood flow so that your heart is getting oxygen as you're exercising. So which of the 4 variables will be part of the constant? Well, the ones that were constant are these first 3 that we set to be constant. And so somehow they are going to interact to inform the constant in this proportional problem. So radius is constant, viscosity is constant, and length is constant. And then what is varying, so the things that are varying are the blood pressure and the blood flow. And I know those are varying because we put in a variety of numbers, we got a variety of answers. Then it asks what type of variation exists between the two variables. Well, we had looked at that when things are directly proportional, they will both get bigger, and that is exactly what has happened here. So we have something that is directly proportional. And we know that something that is directly proportional will have a multiplication relationship. So it asks us to define variables and to write that equation. So I'm going to use this as P for pressure, and I'm going to use this as R for rate. And I know that in general, the first column is always my domain. The second column is always my range. Or if we're using the generic algebra letters, the first one is my X, and the second one is my Y. So because of that, normally I think of equations or functions being in the Y equals format. So I want to start with the flow rate equals some constant times the pressure. And that K times is because these are proportional. And so there is a multiplication relationship between them, and that's why they both go up together. So letter F is where I have to do a little bit of algebra and then a tiny bit of math for G. So letter F, it says use a pair of numbers to find the constant. Well, I can use any pair of numbers. I am going to pick the first pair of numbers. So the first pair of numbers is the first row across my chart here, and that is telling me that when the flow rate, so plugging that in for my R, the flow rate is 3.6353, when the pressure is 20. So I'm filling in the R and the P, but I do not know K, the constant. And so in order to solve for that, I will literally just divide by 20 because division is the opposite of multiplication on both sides. Those cancel over here. And so then I did that on my calculator, 3.6353 divided by 20. And I got the constant of 0.181765. And you may round that off somewhere. I didn't give any rounding directions here, so I'm giving you all the digits that I see on my calculator. And so then the final one, it says use your equation to predict the flow rate when the blood pressure is 220. So blood pressure of 220, well, that would be even higher than 180. So I'm expecting an even higher flow rate. And I'm going to use my formula, which is up here. I'm going to use my constant, which is the next one down. And so the rate that I'm going to predict is going to be the constant, 0.181765, times this pressure of 220. And so I just go to my calculator, let it do the math for me, and I get an answer of 39.9883. Now again, if you round it off your K, your decimals may be a little bit different there, but very close to 40. So 39.9883. And that makes sense to me in that my blood pressure went up, and so my blood flow rate went up, and that's how these two are related. If I go back and look at what the French scientists discovered, I see that blood pressure here is on the top of the fraction, and so the blood flow is this constant that he has, which is for all of the variables together, times the pressure. And so I do see that that has that multiplication relationship in his formula as well, which gives me a little bit of confirmation about the work that I have done on this. So whenever we see both variables increasing like we did here, that is where we have this directly proportional idea which we set up with a multiplication problem. And those are the really big takeaways from this video.